So welcome to lecture 26 of MCS 472 on industrial mathematics and computation. So today we will see how to realize filters as electric circuits, filters that can be defined as solutions of ordinary differential equations. So in this lecture we make the connection with what we've seen in the last chapter on ordinary differential equations, and we also make the connection to what we covered much earlier in the course on the filters, namely low pass and high pass filters. And we will end with stability, with a proposal for a project concerning traffic. Okay, so let's first look into the connections of ordinary differential equations with signals. So signals are continuous functions, and filters are generalized into what we call a plant, or you could say also a process. So what is a plant? A plant is linear, time invariant, and causal. So it's a mapping that has all these three properties, and that maps a signal into another signal. So filters are one class of examples of plants. We have covered damped harmonic motion as a model for a car suspension mechanism. And in this lecture, we will see the connection with electric circuits. So plants, they cover these three seemingly entirely different areas from signal processing, mechanical design, and electrical engineering. So a linear time invariant and causal filter is entirely determined by the response to the unit impulse. We defined this earlier for discrete signals. Lately, in previous lecture, we generalized this convolution operator as an integral operator. So we can speak of the convolution of two signals. And the little h will give rise to the capital H, which is then the transfer function. Okay, so we have covered the Laplace transform. So the Laplace transform allows to rewrite a differential equation into an algebraic equation. Here we consider a simple first order differential equation with zero initial condition. So then we don't have to worry about the initial condition anymore. So this is transformed in a transfer. This is transformed in the frequency domain, where what connects the input, so the transform of the input, the capital U, to the transform of the output, the capital Y, is the function which has s plus 1 in the denominator. And the root of this denominator, the negative one, shows up in the convolution in the left hand here of the convolution operator, where we are multiplying by the e to the power negative 1 times t. So this also summarized what we did last time with the Laplace transform. Let's see what that buys us now. Let us consider the same differential equation again. So this is a differential equation which we now see as a plant. So we have an input. The right hand side of this differential equation is a function changing in time, which is our input. The solution to this differential equation will be the output. So, and to see what it does, consider two very different inputs. So we consider two functions which represent both signals. So the first, and they are both described and defined by single sine functions. So the first one is a very slow moving sine function. It takes 1000 seconds to complete one complete cycle. So that's a low frequency signal. The other one does 1000 cycles in 1 second. So that's a high frequency signal. So we will give these two functions as input to this differential equation and solve it and see what we obtain. Here is the input. So here is the low frequency signal. It's just a sine function. But what is important here is the horizontal axis. Notice that we have one complete cycle at 1000. So time here is the horizontal axis. At 2000, we have two complete cycles. Okay. Then we have the same sine function for the high frequency signal, but note that now the t-axis has an entirely different range. So at t equals 1 over 1000, we have one complete cycle, and 1 over 2000, or 2 over 1000, we have two cycles. So in a way, these signals are entirely different, but when you plot them, you adjust the range of the t-axis accordingly. Okay, so I will use SymPy to solve this. So we are in the setting of the last chapter, and we can solve this symbolically. So I will define the signals as functions, so that was used for the plot. Then for the symbolical solver, we use symbols, one symbol for time, another symbol for the differential, for the variable in the differential equation. So then we set up the left side of the ordinary differential equation. So we can do this after we have defined these symbols. And the initial condition stating that at time equals 0, we have no displacement. Okay, so then for the low frequency input, we are going to evaluate the function, the low frequency function defined at the first line here in the code, at the symbol. So the t at the beginning is different than the t towards the end. So the next to last line gives a symbolic equation, not a function. So, and then we apply dsolve, passing the initial condition to the solver along with the equation. So there is a Jupyter notebook that is posted with this lecture. So in some sense, this slide here summarizes the instructions that you need to solve the differential equation and to plot the results. Okay, so let's look at the output. So what is the output? So for the low frequency signal, we obtain a sine function back. So the first coefficient 0.9999 is very close to 1. Also the t over 1000 times 2 pi. So you can kind of see that we have the same frequency back. So then there are two extra terms with much lower coefficients. So there is a cosine term there. So there is an oscillating term, and then there is a decaying term. So just by looking at the shape, at the output, the numerical output of the solver, we can say that what is the output is again a very low, the same signal, again at a very low frequency. There is some extra terms there, but when we look at the signal, in the meantime, when we plot it, there won't be any difference. On the other hand, if we keep the same ordinary differential equation. So I'm now in the second part of the experiment. I'm taking the high frequency signal. So I'm taking the same ordinary differential equation, the same left side, but now I'm at the right side, I'm putting the high frequency formulation. If I solve it now, then you see that the sine function, the first term, comes with 10 to the power minus 8, and that's really, really tiny. So also the other two terms have very small coefficients. So what this actually says that so we will see this ordinary differential equation as a formulation of a filter. So if we solve this ordinary differential equation, we actually get something that is very, very small. So our high frequency signal has disappeared. So here is the plot of the output of the low frequency signal. And if you look at so you have to believe me that it is that, because on the plot you don't see any difference with the sine function that we considered before, the sine function that makes one entire cycle for t equals 1000, and 2 cycles for t equals 2000. So the Jupyter notebook shows the coherence in the experiment. So this is the output for the low frequency signal. On the other hand, now if you look at the output of the high frequency signal, remember this 10 to the power minus 8 that came in there. So the sine function is completely gone. What you actually now here see is the noise. So you see the added stuff that was a cosine. So we have one complete cycle at 1 over 1000, or so this cosine also runs at the faster frequency, but it is very, very, so in addition to looking at the numbers on the horizontal axis, you see the numbers on the vertical axis. So if there wouldn't be that automatic scaling, if we would set the horizontal limits to be 0 and 1, then we would not see this plot. And then this plot would just be a horizontal blue line. Okay, what did we do? We constructed a filter that actually will only pass the low, that is a low pass filter. So that's actually the point of this computational experiment. As an exercise, you will consider the high pass filter, where you have the same left side as the ordinary differential equation, so the same left as here on this slide, but as the right you pass the derivative of the signal. So then the differential equation represents a high pass filter. So to verify this, you will solve the ordinary differential equation. You will solve this problem for two input functions. Once you take as input the low frequency signal, and once you take the high frequency signal. And you verify indeed that the low frequency signal for this filter will disappear, whereas the high frequency signal will remain. So we have the mirror situation. Okay, so that's essentially the main point of the first part, so that one can see filters as solutions of ordinary differential equations or ordinary differential equations. They model, they are so fruitful models for so many things. So they model also what filters are doing. Okay, this is about cascading plants. So what you can do is you can consider a sequence of two differential equations where you have the low pass, so we have the same left hand side, but to the first differential equation acts as the low pass filter, and then the second differential equation takes as input the output of the first differential equation, and that will then be the high pass filter. So what will happen if you would solve the sequence of two equations, and actually if we have made the first exercise, we know what's going to happen. So what happens is that signals at very low frequency are going to be removed by the second differential equation, whereas the first differential equation removes the high frequency signals. So what we have effectively constructed is a band pass filter. So only signals within a certain range of frequency will pass. Okay, so modeling this as a differential equation is kind of cumbersome. But the main point is that we introduced the Laplace transform. The main benefit was actually to simplify, to solve differential equations as algebraic equations. When we work in the frequency domain, uh, connecting one plant after the other, one filter after the other, leads to is actually the product of the transfer functions. I mean, composing plants, so making more complicated processes from simple processes, is done very simply in the frequency domain. So we have the transfer function of the uh, bandpass filter as the product of the transfer function of the low pass filter with the high pass filter. So this is our first example of what we call plants in cascade. So this is what I just said is repeated here because it's so important. So the summary of this experiment, of this computational experiment, is shown with the picture here. So we had the low pass filter followed by the high pass filter. That's an example of two cascading plants, and the transfer function of plants in a cascade is the product of the transfer functions of the components in the cascade. So that's the main point. And what does this buy you? So this is our second exercise. So we consider four components. So there is an amplifier with gain -5, so it's an inverted amplifier. We have an integrator. We have a convolution, and then we have a 3-second delay. So the plant, what the plant does is described in these 4 bullet points here. The diagram shows the components with their transfer function. Then the transfer function of the cascaded plant, of the entire plant, is then neatly written down as this product of these 4 transfer functions. The exercise asks you to compute the time domain version of this cascading plant. The hint is to use SymPy, where we can use the inverse of the Laplace transfer function. The main point of the exercise is also to show the advantage of this approach of working with products of transfer functions to design composite plants. Okay, so we are halfway in this lecture. Let us now look at circuits as examples of plants. So any circuit is made out of three basic building blocks: a resistor, a capacitor, and an inductor. This is shown here with the symbols. So we have voltage that runs across this, and there is a current through these elements. You see the resistor has this ratio over the voltage and the current. We have in general, the ratio of the voltage over the current is what is called the surge impedance of the device. What will be important in the realization is the symbols that we will be using. So the V over the I is kind of using a similar role as what we did with the ratios of the Laplace transforms. So the Laplace transforms of the output over the input. So we have the symbols R, C, and L for the characteristics of the resistor, the capacitor, and the inductor. This comes all with units, so there are units associated to this. What is important in this mathematical-oriented course and computational-oriented course is that we can formulate the Laplace transforms, and you see already the S coming in there. So we can place these building blocks either in series or in parallel. So here you see the diagrams. So we have the two building blocks in series and then the other two in parallel. So these two constructions lead to expressions for the surge impedance, either as the sum of the transfer functions or the sum of the inverted ratios. So these are the two ways to construct them. We will consider this network where the block diagram suggests the Laplace transform of the input, and then you see the Laplace transform of the output there. So this network has the transfer function where we have the transfer function of the second component over the sum of the two transfer functions. So it's a non-trivial exercise to prove that this is indeed the transfer function. So we will use that result to show the realization of our low pass and our high pass filters. Okay, so how does this happen now? So we have this network. So in some sense, you should probably have stared a little bit longer at this network. So what do we have for Z1? We have the resistor. And then for Z2, we have the capacitor. So the Z2 has this 1 over the ratio. Perhaps I should, actually also for my own benefit, I should go back. So here you see the ratios of the resistor and the ratios of the capacitor. So then we are looking at this network here, where the first component is a resistor, and then the other component is this capacitor. So now we are using the formula of the exercise, where we have the transfer of the second component over the sum of the two transfer functions. And that leads to 1 over RC times S plus 1. Remember, the transfer function of the low pass filter was 1 over S plus 1. So our differential equation used a very simple coefficient 1. Here, depending on the characteristics of the resistor and the capacitor, we can modulate depending on which frequencies will be eliminated by this low pass filter. What is the threshold? Okay, very nice. So we have the ordinary differential equation that described what a low pass filter did. We also covered earlier in this course, in the discrete setting, a low pass filter. Now we see the realization with an electric circuit, which in turn is another illustration of a plant. What does the circuit do when you put a current through this? Okay, so then the other high pass filter is the mirror, and in this we use the same network and we swap the resistor. So where we had the resistor, we now have the capacitor, and where we have had the capacitor, we now have the resistor. So we are using the same formula. So now the R appears in the numerator, and we have R plus the Z2 in the denominator. And now you see that our transfer function is RC times S over RC times S plus 1. Take again R and C equal to 1, as in our very simple ordinary differential equation, where we started and we find the transfer function of this circuit, so of this plant, which realizes a high pass filter. Okay, so the textbook contains other examples. Also, I'm going to cite other references where you can see other examples of circuits, but these are the two main important ones that make us realize the connection between filters and ordinary differential equations. Okay, so in the last 10 minutes I will describe stability. So this chapter goes towards control. We want to control a plant. When is a plant stable? A plant is stable if a bounded input gives bounded outputs. So we have the observation that if your impulse response is decaying, and we are looking at linear, time invariant, and causal plants, entirely determined by the impulse response. Now, for a stable plant, these responses will be decaying. So that's the reason why we had this exponentials there with the negative exponents. Okay, so we need one more definition before we can formulate the criterion for stability. So our transfer functions have always been rational functions, the ratio of two polynomials. Now we say that the roots of the denominator are called the poles of our ratio, of our quotient. So the poles are where essentially the transfer function is not defined as an algebraic expression, so there is an asymptote there. So this is where things are getting interesting. So this is what characterizes the plant. So that's an interesting perspective. Where the transfer function is not defined algebraically, or in classical number sense, because you have asymptote, this is where we actually are going to characterize the behavior of the plant. Okay, so what is now the stability criterion? So we have a plant with a transfer function. So when we think about plants, we write our transfer function with a capital P. Although we can also, with filters, we were using the capital H for the impulse response. So we say that the plant will be stable if and only if all the poles have a negative real part. So the roots of a polynomial, so even if that polynomial has very nice real coefficients, the roots of a polynomial may be complex with non-zero imaginary parts. We care about the real parts, because why? Because the real parts will show up in the amplitude. So whenever we have complex poles, we have oscillating behavior. We have sines and cosines coming in. The real part is going to appear as the exponent in the amplitude. And we want this amplitude to be decaying. So the transfer function is going to tell what the unit impulse is doing. So if the unit impulse is not decaying, then the plant will not be stable. So one can show this via the partial fraction decomposition of the transfer function, and then explicitly write out the form of the solution in the time domain. So in a way, I already interpreted the theorem in terms of the amplitude of the signals that come out of the impulse response. So here is a simple example where we solve the quadratic equation for the form here. So an exercise could be to look at the solution in the time domain, really see that a plant with this transfer function is indeed stable. There is an interesting algebraic property as well. What can you say of a quadratic equation that has all the coefficients positive? What is then the sign of the real parts of the roots? Is it so that you can make a very conclusive statement that, say, if all the coefficients of the denominator of the transfer function are positive, then the plant is stable? Can you make a statement like that? So that's actually the purpose of the exercise. Okay, so far of the theory, the terminology, and what we've done so far is very nice. So like in any very good mathematical course, we see that all the stuff that we have learned so far, we are in the end of the 9th week, we start to understand the connections between signals, filters, ordinary differential equations, transfer functions, Laplace transforms, frequency domains, time domains. So we have developed a nice toolbox to solve problems. But what are the problems now that we can address? So let's go back to the traffic models. So in chapter 9 in ordinary differential equations, we developed a car following theory. In particular, we described the 3-second rule. So that was done by looking at a model for two cars following. So let's consider that model here again. So, but now we are using the terminology of systems. So we have an input function and an output function. So the input function tells us the position of the leading car, and the output is the position of the following car. So, and of course, the car that follows wants to avoid collision, so the acceleration will be adjusted in proportion to the difference in the velocity. So the left side of this differential equation is the change in acceleration with a delay. So there is a delay term there. We gave numerical values for the delay, and we also gave the value for the 3-second rule. So the value for alpha gave the 3-second rule. So the right side of the differential equation is the difference in the velocities between the leader and the follower. So to make the model straightforward, we assume initial conditions is all 0, which sounds a little bit strange. You consider 0 velocity, but don't worry here. We are interested in modeling, and we have now a second order differential equation. You can see that in the model that we ultimately consider, the velocity doesn't play a role because we look at the first order differential equation. And if you think that alpha equals 1, then you say, and tau equals 0, then actually we have already seen this differential equation. So that was the first differential equation that we considered with the low-pass filter. So no surprises here. In mathematics, we always encounter the same characters and the same actors. They often are dressed up a little bit differently. So here there are more parameters in the model. We have a parameter alpha and the delay parameter tau. So in the frequency domain, so when we consider the Laplace transform of the input and the Laplace transform of the output, so you see that you will have s times y of s, and then also alpha times y. So the delay term is expressed with this minus tau times s in the exponential function. Okay, so that's our model. So far, so good. I mean, we actually made this much more complicated. But remember the theorem on the stability. So if we consider the poles of the denominator, then we can derive the relationship between the alpha and the tau. So in chapter 9 we gave very specific numerical values for the alpha and the tau. Do they make sense? And here is now the relation to the industry. And what is the essence of the course actually? The modeling towards industrial projects. Look into the stability of cars following each other. So the moral of this project is, even if you wouldn't attempt it, if you ever get talked into taking part into a platoon of cars, I would recommend that you don't that you don't end up with your car at the tail, because that's not a good place to be. So even if everybody is actually following this 3-second rule, so you can use that 3-second rule also in a first attempt to address this project. So our projects are in some sense open-ended, so there's never a final conclusive answer, closed form, but in the other sense it's also open-ended that we have already addressed this problem. So you can always say something about this. So in the first 5 minutes of seeing this problem, well, go back to the numerical values that gave us the 3-second rule and verify if for these two particular constants the problem is actually stable. So does the 3-second rule make sense? But you will find a general relationship between the tau and the alpha. So in the second part, you consider more and more cars. So initially you can look at, so what this actually boils down to is that you consider a cascading. So initially, so what you will do is you will do like in the beginning of the lecture. If you have 3 cars, you have 2 differential equations. And you have 3 differential equations, and it gets really, really messy if you think in differential equations. But if you think in terms of transfer functions and cascading plants, then actually it comes quite manageable. What you end up considering are products of transfer functions. And you should come to the conclusion, so this is, if you have if you have taken part in a funeral procession or in any other platoon with your cars, then it's kind of natural that the followers further down the platoon have a lot harder time than the others. So that's quantifying this, illustrating this, describing this is the topic, is the goal of this project. Okay, so I do not want to stretch this all the way to the full 50 minutes. What we did today is showing that as mathematicians that everything is connected. So mathematics is the language between very seemingly disjoint topics in information processing with filters, in mechanism design, in electrical engineering, that several very disjoint fields are actually neatly described mathematically. So we covered more. We are now close to the middle of chapter 10 in our textbook, which takes a kind of a mathematical turn. But then if you want to see many more examples of all many fields of engineering, mechanism, filter design, electrical engineering, then the second reference is here also recommended. So thank you for watching this recording. I hope this was interesting.